Biosensors are devices which can measure and detect the presence of chemicals in living organisms, and they're used for everything from drug development to disease tracking. In these biosensors, silica, a type of glass, has become the favored material for the bulbs that come in contact with biological materials to collect information. But the solutions can interact with the surface of the silica bulb and break down the silica over time. In my summer project, I evaluated the degree of erosion of silica in several different buffers and at several pH levels in order to determine which solution conditions will be best suited for research involving silica biosensors. The first step of the project was to make a sphere of silica to be tested by zapping a piece of optic fiber. Then it was immersed in the buffer being evaluated, and the size of the sphere was monitored using whispering gallery mode, which shoots lasers around the sphere and then monitors the wavelengths as they bounce around the glass. As the size of the sphere shifts, so do the wavelengths, and here you can see a peak as it shifts to the right. After some analysis of the data on a computer, a graph like this can be generated, where the red line represents the shift in temperature, the blue line represents the shift in wavelength, and the green line represents the shift after temperature has been compensated for. So the slope of this green line is going to represent the shift in size of the sphere. But there were some other variables that we wanted to take into account beyond the pH level and the type of buffer, namely the hydrophilicity of the sphere. By treating the sphere in Fentone's reagent, which is the reaction you can see here, we attempted to create spheres that were uniformly hydrophilic. After this, we would be able to adjust the level of hydrophilicity by leaving them in the oven so they slowly became more hydrophobic. To test the hydrophilicity of each sphere, we would dip them in water like this. This sphere is relatively hydrophobic. You can see that when the sphere touched the water jumped to less than halfway down the sphere. And when the sphere is pulled away from the water completely, the drop of water that's left over is not very spread and it's relatively small. To contrast, here is a sphere that is more hydrophilic. When the sphere touches the water, you can see that the water jumps to over halfway down the sphere, and the hanging droplet that's left on the sphere when it is completely removed from the water is larger and more spread over the top of the sphere. However, with this part of the project, we could not achieve consistent results. Although we spent a lot of time tweaking the process of the Fentone treatment, further investigation is needed to figure out the best way to treat the spheres. For the purposes of this project, the hydrophilicity of each sphere is noted, but does not impact the overall results, which are broad enough to not be heavily influenced by this factor. So, over time, I tested my spheres in MOPS buffer and phosphate buffer solution, and these are the results. These graphs on the right show the slope of the temperature compensated shift, or the shift rate, versus the pH for phosphate buffer and for MOPS buffer. You can see that as the pH of PBS decreases, the shift rate increases, meaning the size of the sphere is increasing. In fact, at PBS pH 6.5, you can see a positive shift rate of about 0.0004 parts per million per second, which is about 8.5 nanometer increase in diameter per day. This indicates that there is something building up on the surface of the silica, resulting from the interaction of silica with the buffer. For MOPS buffer, you can see that this is happening as well, but at higher pH levels instead of lower ones. At high phosphate buffer pHs, you can see a negative shift, which indicates the erosion of silica. So now the question is, what is building up on the surface? Well, we really don't know yet. Not a lot of research has been conducted on the interactions of these buffers with the surface of silica, so we can't be sure the exact interaction going on here, especially with the phosphate buffer. Despite not being able to conclude what is happening here at a molecular level, we can draw conclusions from this project about which buffers and pH levels will be least disruptive, and then this information can be used to make informed decisions about the design of silica biosensor experiments.